Welcome to the Ocean Vision Summit 2021. You see a poll in progress. Please take it as we go over housekeeping. You are in session 1, Accelerating the Ocean's Power to Sequester Carbon and Reverse Climate Disruption. During this session, please mute your microphone and turn your video off. Speakers will be highlighted, so they will be the focus of the video. If you have questions for speakers, please put the questions in the chat with the word question starting it. If you have a technical problem, please put a technical problem in the chat with technical starting that comment. It's about time for us to end the polling, and to start session 1 will be the Executive Director of Ocean Vision's Brad Ack.
Hello, everybody. Welcome to session 1. I have some slides that hopefully will appear on the screen shortly. While I'm waiting, the title of session 1 is Accelerating the Ocean's Power to Sequester Carbon and to Reverse Climate Disruption. This, in a series of discussions about the biggest problems that we face in the ocean, this is probably truly the largest. And this session is going to be all about different ways that people are experimenting with and examining the power of the oceans to reverse the climate crisis. Next slide, please. The reason that this is so urgent is that the climate emergency is happening right now. It's not something that we're expecting 20 to 30 years from now. Basically, we're seeing enormous climate impacts across our globe on a regular basis, up to 1 a week, according to the UN. And as the temperatures continue to rise, which they will, of course, as atmospheric carbon continues to increase, we see that the risks get higher and higher. Next slide, please. We also can see that the current set of actions that we have to confront this problem are inadequate. The graph on the left simply shows the rise of carbon dioxide concentrations in the atmosphere, counterposed to the numerous international agreements that we've negotiated to reduce them. And on the right, you see the most recent statistical review of world energy, which shows that greenhouse gas emissions are going up, fossil fuel infrastructure investments are going up, and we're still locked into 83% of our global energy from fossil fuel use. Next slide, please. And also, I would argue that the target of a 1.5 degree centigrade change is really an unsafe target. We're at about 1.1 right now, and the climate is dangerously unsafe already for hundreds of millions of people, as well as many other life forms on the planet. And this graphic shows you the sort of severity of impacts at different temperatures from 1 to 1.5 to 2. And you can see in the left that for warm water corals, for example, where we already are is exceedingly grim for warm water corals. And that is true across the board, that this 1.5 target is not some great and safe place that we're all going to be happy with. Next slide, please. Also, that target is unlikely to be durable, and this is because there are these positive feedback loops throughout our planet that, as temperatures warm, are going to continue to emit more greenhouse gases or create conditions for increased warming. So keeping temperature to 1.5 with this enormous amount of atmospheric carbon is really unlikely to be achievable. And the other thing is that the 1.5 target is going to greatly increase damage to the ocean. The two biggest stresses right now to our ocean and the long-term viability of our ocean are greenhouse gas induced. Next slide, please. The first of those is thermal stress, which is basically just the heating of the ocean. We like to say that the oceans have absorbed 93% of all the heat and caused by anthropogenic CO2, which sounds great, like it's buffering the terrestrial environment. Actually, it's creating a slow motion disaster in our ocean, from accelerated sea level rise, intensified marine heat waves, deoxygenation, interruption of currents and mixing, and poleward migration of marine animals. It is a natural disaster that for most is out of sight and out of mind, but those of us in the ocean sciences community know this is happening, and we know right now that we have no answer to it. Next slide, please. The second big stress from too much carbon in our biosphere is ocean acidification. The oceans have absorbed directly about 30% of all CO2 emitted to the atmosphere, which is triggering oceans to become more acidic. And the graph on the left shows the red line atmospheric carbon, and the blue plots are reduced pH. And of course, this affects any ocean life that forms shells and has enormous amounts of unknowns as this curve, the red curve, continues to go up. Next slide, please. So we really need a new climate plan for the ocean. Our current climate plan is not good enough for the ocean, and it's really not good enough for humanity. We have focused on decarbonization for 45 years, which should remain central, but we now need to recognize that decarbonization alone is not going to bend these curves, and we're going to need to do more, particularly to clean up the legacy of 200 years of carbon dioxide, methane, and other greenhouse gas pollution. And I would argue as well, we need to begin to focus our attention on what I call ecosystem life support, which is keeping key components of the system functioning while we bend the curve on global carbon concentrations. Next slide, please. So decarbonization remains critical, but from the 1.5 report that the IPCC did, they basically call out that the transitions needed are unprecedented in terms of the scale and the pace that they're going to be needed. Next slide, please. So we know that we have to add something to the mix, which is referred to commonly as negative emissions. I would frame it to all of you as the cleanup of legacy pollution. We do this all the time, such as through the United States EPA Superfund program, where we have put toxic chemicals into the environment over years. We clean them up. For some reason, the ocean sciences and ocean conservation community has had a hard time wrapping its mind around the fact that carbon dioxide at the extreme levels that we find it is a pollutant. It's actually classified as a pollutant by the EPA, but we're not treating it as a pollutant. And we need to begin to clean it up. Next slide, please. In fact, the same report that I referred to, the 1.5 degree report, had a series of 400 plus models. All of the models that led to limiting global warming to 1.5 with limited or no overshoot all projected pretty significant amounts of carbon dioxide removal over the course of this century, between 100 and 1,000 gigatons of carbon. So that's 100 billion tons, 1,000 billion tons. And again, that's just to get to 1.5, which I would argue is not a safe target for the ocean or humanity. And if we want to go beyond that and begin to reverse this mess that we've made, we're going to have to take out even more carbon. Next slide, please. Ocean potentially has an enormous role to play in this grand endeavor that we face. The ocean already cycles and stores very large quantities of carbon. The ocean has capacity for more. There's about 50 times more carbon in the bottom of the ocean now than there is in the atmosphere. There are a lot less conflicts in the ocean to scale carbon dioxide removal, presuming we can do it safely, than there are on land. And there's the possibility of some pretty significant co-benefits for ocean ecosystems and fisheries. Next slide, please. And there are a number of potential pathways, from the biotic, such as micro and macroalgae, to abiotic, such as alkalinity modification and electrochemical approaches to separating CO2 out of seawater. And this is what Ocean Visions has focused on over the last year, with really further identifying and understanding where we are with these particular pathways and what can be done to determine whether or not they can contribute carbon dioxide removal at the scale that's going to be needed across the globe. Next slide, please. So we have been working on building technology roadmaps for ocean-based CDR. And that basically means identifying what's the current state of technology, what are the most critical obstacles to moving technologies forward towards testing and development, and what are the biggest near-term opportunities to make significant gains. We've convened a lot of experts across the globe over the last year or so. We're really excited to roll these out, and you're all going to get a chance to test drive them. And to tell you more about them, I am very happy to turn the mic over to David Koek, who is the science director at Ocean Vision. David.
Thank you, Brad. And thank you to all of you who are joining today. I'm going to wait just for a moment until the slides come up. Let's see. Okay, can we go back to the introductory slide, please? Great. Thank you very much. As Brad said, my name is David Koek. I'm the Science Director of Ocean Visions, and I'm thrilled that all of you are joining us today as we introduce the Ocean Visions technology roadmaps for ocean-based carbon dioxide removal. Next slide, please. As Brad mentioned, about a year ago, Ocean Visions set out, with generous support from the ClimateWorks Foundation and Schmidt Marine Technology Partners, to develop these multidisciplinary technology roadmaps that were really designed to identify the state of technology, obstacles, opportunities, and priorities to advance a number of promising technical domains for ocean-based carbon dioxide removal. In this first year, we focused on 3 large classes of ocean-based carbon dioxide removal technologies, including macroalgae cultivation and carbon sequestration, ocean alkalinity enhancement, and electrochemical approaches to carbon dioxide removal. And from the very beginning, we recognized that it's not just about the science and engineering, it's also about the public perception, it's about the communications, it's about unlocking finance and investment. And so we also built roadmaps on cross-cutting themes, including growing and maintaining public support for ocean-based carbon dioxide removal and how to unlock finance and investment. Next slide, please. As I mentioned, this process has been underway for about a year. So last summer, we kicked off an expression of interest survey that helped us build out a global database of interested individuals. We held scoping workshops in the fall to identify critical challenges and then reviewed the initial findings with experts in review panels in January. Then we went to work really synthesizing and writing out the content that had been developed through these workshops and surveys. And then we opened up that content for public review. And today, I'm really thrilled to share with you that we're going to be launching these roadmaps on an interactive open web platform. And you'll be taking these for a test drive in just a little bit in the session. Next slide, please. When I say that this was a global effort, I really mean it. We had 189 contributors coming in from 23 countries on 6 continents. And I think that this really speaks to the global interest that's building to not just identify the problems associated with our carbon pollution, but to act on accelerating solutions to address that problem and stabilize our climate. Next slide, please. And so these are what the roadmaps look like. When you get to the landing page, and we'll share the link with you in just a little bit after the invited speakers, you'll see 5 roadmaps. And today we're launching the macroalgae cultivation and carbon sequestration roadmap. The other 4 roadmaps will appear over the next few weeks. Next slide. And for each roadmap, we break down the information into basically 4 domains: the state of the technology, the critical obstacles, the development needs, and the first order priorities. And then within each of those, there's subcategories. And all of this is interactive, all of it's clickable, you can explore it, it should be fully functional, and it'll really give you a chance to dive in and find out what we found. Next slide, please. When you click on one of these subdomains, you're brought to a page as an example that you can see on the left-hand side here, the state of the technology. And we use this accordion design to allow you to be able to move into identifying the piece of information that you'd like to identify as quickly as possible. So for instance, if you were only interested in looking at the environmental co-benefits, you could click state of the technology, environmental co-benefits, and then that accordion design would open up and you could read about the environmental co-benefits. On this right-hand side here, I'm showing you what some of the textual information looks like for the overview section. And as you can see on the right-hand side of the right panel, you can see who last updated the roadmaps, because these roadmaps are intended to be living documents that will be continually updated by a global community of curated individuals to make sure that this information stays current. Next slide. And this functionality of continually updating the roadmaps is something that we're also going to be introducing in the next few weeks. So shortly, we will open up the feature where interested users can sign up to become expert content contributors. And when that happens, they'll be able to update the roadmaps themselves. And here I'm just showing you what the back end of that might look like in the future. So we're really excited for this feature, and we're really excited for the potential of this feature to make sure that these roadmaps stay living documents, stay at the cutting edge, and are really capable of helping to drive progress as quickly as possible to help accelerate the research and development of this field. Next slide. So I'd like to spend a few moments sharing with you some of the first order priorities that we found in the pursuit of our macroalgae cultivation and carbon sequestration roadmap. And you'll have, again, more of an opportunity to explore these, but I just want to highlight some of them for you right now. By far and away, the biggest outcome of our year-long endeavor was a really, really resounding need for controlled field trials that are capable of answering questions about carbon sequestration rates, their permanence, their environmental co-benefits, and any environmental impacts. And so in this set of first order priorities, we lay out a series of critical needs around getting ourselves to the point of being able to do controlled, transparent, collaborative field trials. And to do that, we also need these tools for autonomous operation. We lay out sensor development needs and needs around harvesting and quantifying of carbon sequestration. We also identify a number of industry partnerships that we think could really accelerate progress in this field by helping us move down the learning curve more quickly and helping to take advantage of the lessons learned in industries like offshore wind and aquaculture. We identify a number of things that need to happen to help unlock investment in this field, including things like doing some of the market research, building out business development plans, and strengthening the carbon markets. And then we also talk about some of the steps that are needed to grow and maintain public support. Next slide, please. So we have a really action-packed agenda for you today. For about the next 45 minutes, you're going to hear from a series of invited speakers who are going to talk about the potential and growth of ocean-based carbon dioxide removal. And they're also really going to speak to the potential of these roadmaps to accelerate progress in the field. After that, we're going to come back, we're going to have a panel Q&A, and then we're going to move into a really interactive part of the session where we're going to allow you to take these roadmaps for a test drive, and we're going to send you into small Zoom breakouts with some specific instructions about how to navigate through the roadmaps. Then we're going to come back all together and hear from some technologists who are building new ocean-based carbon dioxide removal ventures. And then we're going to come back together as a community and share our feedback on these roadmaps together, because we're really interested in hearing from all of you. So like I said, we're about to move into this section with invited speakers, and we have 4 recorded talks. But before that, it's my real distinct pleasure to introduce Dr. Jan Mazurek, who's the Senior Director of the Carbon Dioxide Removal Program at the Climate Works Foundation. And Jan's going to speak to the real potential of these roadmaps to help grow this field of ocean-based carbon dioxide removal. So with that, I'd like to turn it over to you, Jan.
Thanks so much, David, Brad, and AGU for hosting this, what I hope will be a very productive and informative endeavor. So as David noted, my name is Jan Mazurek, and I'm a senior director at the Climate Works Foundation. We are an organization that catalyzes philanthropic ambition. So what that means is we seek to help educate other climate philanthropies in this space and provide comfort, outreach, whatever is necessary to leverage greater investments in solving the climate crisis. And we're very delighted that any number of new funders have entered the climate mitigation space in the last year. Including Bezos Earth Fund, among others. But again, as I'm going to talk about in this presentation, the need is absolutely enormous, and as of yet, because this is a very novel area, the level of funding ambition remains modest. So I'm going to walk through basically what climate mitigation and conservation funders are spending and contrast that to the amount of ambition that philanthropy is putting towards removal. And I say this because we manage at Climate Works a very small but ambitious effort to look at removal across all domains. So we look at natural solutions, engineered approaches, and most recently with support from the Packard Foundation and others, the ability of oceans to remove historic carbon dioxide. Next slide, please. So climate mitigation refers to all of those things that Brad talked about, absent removal. So avoiding future emissions, but not removing legacy emissions, as well as neutralizing those legacy emissions that will remain after mid-century from long-haul aviation and other sectors. We know from our own analysis using the GCAM model, as well as those models that inform any number of other interventions that Brad referenced, that we need to achieve about 10 gigatons of removal per year by 2050. We also know that as we are more successful in the terrestrial applications, the oceans are going to give some of that excess back up that they've been storing. So this is an enormous undertaking. Climate mitigation to date spends about $1.6 billion a year on things such as decarbonizing the power sector, driving fossil out of transport, electrifying those portions of transport that might be electrified, more recently focusing on very thorny questions around tough to decarbonize industrial sectors such as cement and steel. And then, of course, in the oceans area, we have very, very long time, multi-year conservation commitments from any number of other philanthropies. I will say that climate change mitigation, although the $1.6 billion number per year looks very large, it still constitutes less than 2% of all philanthropic giving. Next slide, please. So these two pie charts or little pack people put in perspective how much money flows to removal as opposed to mitigation. So again, mitigation is avoiding new emissions. Removal is bringing legacy emissions from the last 200 years, as Brad noted, back down to earth, and then neutralizing some of those tough to decarbonize sectors. These are not rivalrous endeavors. These are both now, unfortunately, necessary because, as Brad mentioned, we've been about 40 years too slow to the task of mitigating at the level of ambition that's been necessary. So here you can see that funding for all removal, terrestrial, the engineered approaches such as direct air capture, as well as the more novel area of oceans, constitutes roughly about 6% of all climate mitigation support from philanthropy. That is the pie chart to the left, and on the right, I put into perspective how much ocean removal that is. So now with the new support from the Bezos Earth Fund, aimed largely at natural removal, but also some ocean applications, we still see that Ocean removal funding is approximately less than, around 0.5% of all climate mitigation funding. And this is all for 2019, which is the most recent year for which we have data. Next slide, please. This is just another way looking at the challenge. So foundation support, for all oceans related work comes to about 650 million. And of that, ocean removal receives about $3.5 million a year. So it's less than 1% of all ocean conservation funding. And again, as Brad noted, there are, one of the chief obstacles to increasing funder ambition are just legacy issues around ocean dumping that cause an enormous amount of concern. And I hope we can get to that at some point in the session today, just the perceptions around ocean removal and how to provide greater confidence in the philanthropic community around this. We certainly hope that ocean visions and the roadmaps will be one important and key area for doing that. Next slide, please. So in conclusion, and I raced through this pretty quickly, the need is enormous, and the resources available to address the challenge are minuscule, but we hope growing. That's part of my job here at Climate Works, is to marshal that funding. But I will say in closing that I think one of the big challenges that we face in climate philanthropy is that funding science is typically not in our wheelhouse. That's something that we leave to the public sector here in the US, the federal government, to undertake. And so I'll say that we're extremely proud to be able to help support the Ocean Visions road mapping effort. And in addition, we're also funding a National Academies workshop on this similar topic, which we hope will be wrapping up and publishing later this fall. And of course, the purpose of all of this is to really educate decision makers inside the Beltway and elsewhere to free up more money to fund the vital research and pilot studies that David referenced. It's not something that we do, but what we do is take our minuscule resources and try to really catalyze ambition. So I look forward to working in partnership with all of you here toward that aim. And thank you so much for your time. Look forward to circling back later on in the session. Thanks.
Okay, can we bring the camera back to me for a second, CJ? Thank you. Thanks, Jan. Thanks so much. And without further ado, I'd like to introduce our 4 invited speakers. So we have Dr. Roger Haynes from the Lawrence Livermore National Lab. We have Dr. Jessica Cross from the NOAA PMEL Pacific Marine Environmental Lab. We have Lisa Suetoni from the Natural Resources Defense Council, and we have Kevin Tidwell from the Grantham Environmental Trust. And each of these speakers are going to provide context that's going to build on Jan's talk and provide some clarity about how the roadmaps are going to help drive progress in this field. So without further ado, could we please launch Roger's talk?
Hi, I'm Roger Haynes. I'm going to talk to you about negative emissions, why we need them, and how we might be able to get them at large scale. First thing I want to talk about is the overall need for negative emissions globally. We've all seen this curve, business as usual, and we all know the very negative impacts it's going to have on our climate. If we want to reach allowable temperatures, in this case 2 degrees C, I plotted here, we're going to have to reach net zero sometime this century. Of course, 1.5 degrees C is even harder. But when we look at all the things that we have available to us, all the things that we can use to eliminate emissions, to eliminate fossil fuel, increase efficiency, it's only the field in brown. It's not enough. What else is missing? Well, there's other greenhouse gases and CO2 that we're simply not going to be fast enough to get rid of. We're not going to get rid of it in time. Some of these things, pretty familiar. Airplanes, we all know what problem that is. But a more insidious one perhaps is agriculture, not the fuel to drive the tractor, but the nitrous oxide that's coming off the fertilizer that the tractor's spreading. Are we going to do without fertilizer in our agricultural work? Probably not. And of course, we're all familiar with the problems with methane from cattle and other natural methane emissions. These things are going to be very hard to get rid of, including refrigerants and other CO2, other non-CO2 greenhouse gases. The net effect of this is going to be that for the things that we can't get rid of at the point source, we're going to have to offset them by eliminating other CO2 from the atmosphere, by net removals of CO2 from the atmosphere. And those net removals are going to have to be very large. By 2050, we're going to have to be removing about 10 billion tons of CO2 per year from the atmosphere in order to make up the difference. 10 billion tons is twice the size of today's oil industry. We handle 5 billion tons of oil today worldwide. We need to double that amount in order to clean up the atmosphere. Then just in 2050, it's going to continue increasing beyond that point. And we love to think about these things globally, like I was just talking about. But I think it's more instructive to think about economies or regions or businesses, things that can actually take action. The problem is there is no global authority that's going to tell us how to manage our economy, or like I say, God's not going to come down and tell us how to do this. But businesses can do it, states can do it, regions can do it. Businesses are going to be very important because of their own ambitions to be green and to get us to do business with them. And the good news is that this kind of ambition is growing rapidly. Just a few months ago, it was 22 nations and regions, and now it's 34. 13 American states, more than 1,100 global businesses, and pretty exciting, more than 60% of today's global emissions are covered by an ambition to get to net zero. Now, I distinguish an ambition from a plan. So let's talk about how we can actually do this. How are we going to remove CO2 from the air? What are some of the mechanisms that we can use? And I'll talk about some of the ones that are already underway and come around to oceans at the end. But of course, most of this things you're going to hear today are about oceans. Well, trees, very, very important. They're basically a promissory note. When you plant a tree today, it doesn't begin absorbing a lot of CO2 for many years, and it won't hit its stride for decades. So they're basically a promissory note. And one of the big issues with that is that our forests today in many places are actually emitting CO2. We've heard that the Amazon may be emitting CO2 now. These are the only numbers that I have that I can actually show you a graph for the forests of Canada. And for the last 2 decades, the forests of Canada have been emitting carbon dioxide, not absorbing it. That's pretty scary. Why is that? We all know about insect kill, drought, fire, of course. The fires in last year in California burned enough forest that they emitted more CO2 than the entire economy of California. Those forest fires doubled our emissions. Now you can say those are natural carbon emissions, but they're not net zero because it will take decades for those trees to regrow and remove that CO2. Again, they're actually increasing the CO2 in the atmosphere for the short term when we really care, when it really matters. And one thing we can think about is using biomass waste as a place to start removing CO2. And in particular, those trees that we're going to have to thin, the forest that we're going to have to try and return to its natural state by mechanical thinning, why not use that material as a way to remove carbon from the atmosphere? And this is a thing that the models call bioenergy with carbon capture and storage, BECCS. I contend that BECCS is a pretty good idea if we use waste material. If we're growing new material to do that, then it becomes a very questionable idea, but there's an enormous amount of waste, probably 1 billion tons worldwide that could be used to remove as much as 2.5 billion tons of CO2 from the atmosphere. And the interesting thing about that is we think about wood and other bioproducts like that as an energy source, but they're a crappy energy source. They're a really good carbon source. And if carbon is valued appropriately, which I contend is $100 a ton, I think that's going to be the real price that it's going to cost us to clean up the atmosphere. At $100 a ton, the blue line, we see the CO2 value as it increases rapidly, gets past the energy value of wood or other biomass. So what we can think about is that a trailer full of wood chips is nearly 50% carbon by weight. Terrible energy source, great carbon source. So we should be emphasizing removing carbon with biomass instead of creating energy. Not that we can't still create energy with it, but that shouldn't be the first concern. Soils are a really important part of the next picture. Agriculture has depleted our soils. and depleted them to an enormous extent. Sanderman's worldwide assessment shows that we've lost on the order of 487 billion tons of CO2 equivalent from our agricultural soils. If we could put it back tomorrow, we'd be done. We wouldn't have to do anything else. But of course we can't. We can't put it back that fast. We don't really know how to do it. So we need to speed this up. But this is going to be a huge source of CO2 removal when we figure out how to do it well. And of course, there's machines. Everybody thinks that direct air capture is pretty sexy, and it is because it's very straightforward. Here's a machine, it removes CO2 from the air, that's the problem, and we understand how to do that. In doing that, we're going to have to do something with the CO2 and all of these methods that I've just mentioned. And putting that carbon back underground in the form of CO2 is going to be important because we're just not going to be enough natural sources to make up for all the mechanical things that we've done to put CO2 into the atmosphere. The good news is that CO2's properties are very similar to oil when we can put it very deep in the earth. It can be stored in the same places safely, and the technology and the jobs to do it are very similar. And this is good for the transition of jobs away from oil. The oil age can turn into the storage age. And when geologic storage is used, it's very, very deep, and it puts CO2 into the same rocks that held oil for millions of years. And when the CO2 has very similar properties, we can expect that that CO2 is going to stay in those rocks also for millions of years. And this is something that's been tested extensively. Just in the United States, we put 14 million tons underground in experimental programs, and we haven't seen any leaks. So this is something that's going to work well when you have a bunch of CO2 that you do need to store. A method that's just coming online that we're going to think about a lot in the context of oceans is mineralization, using the rocks in the Earth's crust to absorb CO2, gigantic capacity, just shown in red, just the rocks in California that are capable of absorbing CO2 that we call ultramafic rocks. One of those is serpentonite. This is a picture of a serpentonite terrain in California and the chemistry of the CO2 absorption. Globally, these kind of rocks absorb about 1 billion tons a year. It's really actually kind of hard to get to pin down that number, but it's probably 1 billion tons of CO2 a year. The rocks in this picture that I'm showing here, just this frame, this block of rock, when it's fully reacted, will have absorbed 1 billion tons all by itself. Gigantic capacity. But again, just like soils, we have to figure out how to speed it up. Interesting thing happens to that. It doesn't just turn into magnesium carbonate. Once that magnesium carbonate is formed, it rains, it even rains here in California, and the magnesium and the bicarbonate ions go downstream. The silica stays behind, and that alkalinity heads downstream to the oceans. And in the oceans, it buffers some of the CO2 that's been absorbed by the ocean. And this is one of the most critical things that mineralogy is going to be able to provide for us, is an ability to offset some of the CO2 that's absorbed by the ocean. Now, some of the talks you'll hear today will talk about this kind of a process, increasing the ability of the CO2, the ocean to absorb CO2. It's 6 of one, half a dozen of another. The same amount of CO2 gets absorbed, whether you consider it, as I did, as being absorbed initially by the rock, or when you consider that this addition of alkalinity to the ocean allows the ocean to absorb more CO2. I prefer to think about it in terms of the rocks because I like to buffer the ocean and offset the effects of CO2 that's being absorbed and acidifying the ocean. And of course, the same thing happens either way. The benefit is that we end up with a less acidic ocean and more CO2 removed from the atmosphere. I want to finish by encouraging you all to keep a big tent. Like all of these approaches, please. We're going to need them all, and then we're going to need more. It's very easy when you get involved in creating a new technology to think that yours might be better than somebody else's, or it might be more important. Heck, we're going to need them all. They're all important, and we're going to need to all embrace them and help each other succeed. With that, I hope you enjoyed the symposium. Thank you.
Good morning, everyone. My name is Jessica Cross, and I am a researcher at the NOAA Pacific Marine Environmental Laboratory out in Seattle, Washington. It's a pleasure to join you all this morning to talk about NOAA's interest in ocean carbon dioxide removal. I'm here representing a group of internal researchers from a recently established NOAA Carbon Dioxide Removal Task Force, with the key task of evaluating what role the agency should play with respect to emerging carbon dioxide removal science, what existing capabilities can be brought to bear, and what new capabilities would be needed should the agency be called upon to fully engage carbon dioxide removal research. While the agency does not yet have an official position on carbon dioxide removal yet, we recognize that much more research is needed before the agency can deliver the science-paced, policy-relevant tools and information products called for in the coming years as identified by a recent study by the National Academy of Sciences, Engineering, and Math. According to the IPCC Special Report on 1.5 degrees Celsius, stabilizing climate change at atmospheric temperatures even higher than those that we experience now is going to require negative emissions, technologies that remove greenhouse gases from the atmosphere. This figure from UNEP summarizes the need for negative emissions. The yellow line indicates the business as usual annual greenhouse gas emissions over time, while the red line indicates the emissions limit that would allow for 2 degrees Celsius of climate warming. The shading in the background indicates the techniques necessary to pull the yellow line down to the red line. Obviously, Plan A is to deploy conventional abatement technologies such as a shift to renewable energy sources, shown here in the green shading. However, the IPCC acknowledges that it will be difficult to shift away from some fossil energy and other greenhouse gas emissions. To offset these stubborn annual emissions, we will need carbon dioxide removal technologies, seen here in the blue shading, to achieve our climate goals. It's going to be extremely difficult to generate the negative emissions at the scale required here. The IPCC suggests that we will need to be removing 5.5 gigatons of carbon per year from the atmosphere by 2100. At present, these technologies are not mature enough to operate at even a single gigaton scale. Much more research is needed to understand how we could responsibly meet such a target. NOAA's mission is to understand and predict changes in climate, weather, oceans, and coasts, to share that knowledge and information with others, and to conserve and manage coastal and marine ecosystems and resources. NOAA's dedicated scientists use cutting-edge research and high-tech instrumentation to provide citizens, planners, emergency managers, and other decision makers with reliable information they need when they need it. And this is the lens that we bring to the climate adaptation and mitigation work at the agency. This is what makes NOAA unique. We prioritize service and stewardship alongside our science mission. As I said earlier, NOAA has no explicit mandate to study carbon dioxide removal, although this sector of research has obvious connections to a variety of the existing NOAA programs and missions. For example, NOAA currently supports the conservation of coastal blue carbon habitats, participates in coastal zone siting management activities, researches and regulates fisheries, aquaculture, and marine conservation, and of course houses a robust ocean and atmospheric carbon monitoring program for quantifying national and global fluxes of carbon, as well as rates of acidification. In fact, the Precision Carbon Monitoring Program built into the Global Ocean Observing System and the Global Ocean Acidification Observing Network is probably NOAA's most valuable and unique asset for studying carbon dioxide removal. This portfolio of observations can be leveraged to measure and monitor the efficacy and efficiency of carbon dioxide removal techniques, especially if they are scaled to the gigaton level. A broad range of other NOAA capabilities could be oriented to carbon dioxide removal science, ranging from marine ecosystem response research to Earth system modeling. However, before we start talking about gigaton scale carbon dioxide removal as if it already exists, it is extremely important to remember that there are a lot of open questions to answer. I don't expect you to read all the text on this slide. I know there's a lot of it. And many of these open questions that I've listed here have been reiterated by the Ocean Visions roadmaps that we're discussing as a part of this session today. But I want to note that there are significant unknowns, possible co-benefits, like, for example, ocean acidification remediation, and potential environmental hazards, like introducing heavy trace metals associated with some alkaline materials. From NOAA's perspective, there are two important unknowns that apply to most methods of carbon dioxide removal. Most notably, we are not sure how to best measure and monitor carbon dioxide removal projects to verify the amount of carbon dioxide drawn down. This challenge is especially significant for small projects where it can be difficult to detect a measurable change against strong background processes that also modify carbon dioxide removal. There are also open questions about how to track the environmental impacts of both deployment scale single projects and gigatons level industry scale carbon dioxide removal in coastal and in open ocean settings. So it's the measurement and monitoring and the environmental impacts that we're most concerned about. One project that illustrates many of these open questions was conducted right here in Washington State, where NOAA researchers, foundations, and tribal partners worked together on an experimental kelp farm. The team attempted to track restoration benefits for Puget Sound, and a side benefit would have been the detection of carbon removal. What I want you to notice about this time series plot of carbon drawdown is that it is very, very noisy, highlighting how difficult it is to measure carbon drawdown with our current technology and how individual site selection may play an extremely impactful role in the success of carbon dioxide removal projects and CDR monitoring. The inability to resolve carbon removal from the kelp farm is also key to understanding the halo effect of the installation within the sound. So we don't really know what the overall impact of the restoration was at all, positive or negative. Measurement, monitoring, and impact challenges are often intertwined. NOAA has convened an internal group of scientists, as I said earlier, to help articulate the agency's connection to carbon dioxide removal research, including how this work relates to our legislative mandate from Congress and how we can best fulfill the guidance offered by President Biden's new executive order on tackling the climate crisis at home and abroad. Throughout this process, we are assessing the research recommendations made by the broader scientific community, such as the existing and ongoing studies on carbon dioxide removal at the National Academies of Science, Engineering, and Mathematics, the roadmaps shared by Ocean Visions, and the perspectives shared by other public and private organizations such as the Energy Futures Initiative, the Climate 21 program, and the Departments of Energy and Agriculture. NOAA's unique contributions to the broader carbon dioxide removal research community are likely to focus on assessing the effectiveness and the efficiency of proposed carbon dioxide removal methods, understanding what the environmental impacts of carbon dioxide removal may be in the atmosphere and in the ocean, especially related to NOAA managed resources, and in cases where large-scale carbon removal projects are initiated, monitoring and verifying the actual amount of carbon dioxide drawn out of the ocean or the atmosphere. We'll also be working with our stakeholders and partners across the country to ensure that environmental justice, our science, and our stewardship missions are upheld in all of our scientific work. Carbon dioxide removal shouldn't be just cheap or just efficient. Decision makers should also have transparent information about risks and co-benefits that they need in order to determine whether carbon removal is safe, sustainable, and fair. At the recent Earth Day Global Climate Leaders Summit, there was a lot of emphasis on President Biden's net zero targets and the needs for emissions reductions worldwide. Most of the progress towards our national and global climate goals can be achieved through mainstream available emissions abatement technologies that we can deploy right now. However, even Special Envoy John Kerry has acknowledged that net zero may not be enough for us to achieve 1.5 degrees Celsius warming or less. Even if we get to net zero by 2050, he said at this summit, we still have to suck carbon dioxide out of the atmosphere. Pretty succinctly put. As a part of this workshop, I look forward to working with you to assess how NOAA, alongside the broader scientific community, can responsibly achieve our climate goals. Thanks very much for your attention.
This presentation will give a brief overview of the political and legal landscape of ocean-based CDR in the United States. We at NRDC have only just started thinking about this issue, so the perspective I share today is still very much in the early developmental stages. Before I begin, I'd like to thank my colleague Becca Loomis, who helped pull together this presentation. There is no explicit policy framework for ocean-based CDR. At this point, we only have a patchwork of laws potentially applicable to the technologies, and there have been few legal tests of these policies to guide us. But we can make reasonable predictions about the legal obligations for these technologies by examining existing laws. One of the most important determinants of the legal hurdles is the location of the activity. As an example, I'd like to share a snapshot of what the potential regulatory environment might look like for ocean alkalinity enhancement, depending on where it's conducted. If the alkaline minerals were mined on land, there are dozens of statutes that require permits. The big ones include NEPA, Clean Air Act, Clean Water Act, the toxic laws, TSCA, RCRA, and CERCLA, and the Endangered Species Act. But there are more, a collection of state laws. To give you an idea of the legal requirements for mining, for example, we counted more than 60 federal, state, and local permits that the proposed Pebble mine in Bristol Bay, Alaska would have been required to get before beginning operations. If these minerals were deposited in state waters, potential regulations include NEPA, Clean Water Act, the Marine Protection, Research, and Sanctuaries Act, the Endangered Species Act, the Marine Mammal Protection Act, and the Coastal Zone Management Act, along with various state laws. Moving offshore into federal waters, many of the same laws apply. The only additional law would be the Outer Continental Shelf Lands Act, and that's only if the seabed was implicated or impacted in some way. And beyond areas of national jurisdiction, 3 potential international laws might be invoked: the UN Law of the Sea, the Convention on Biological Diversity, and the London Convention. The point here with these past slides is that location of technology matters. To take a closer look at these laws, let's focus on the regulatory landscape in U.S. waters. This table displays the existing federal regulatory landscape for direct ocean and coastal impacts at a glance. You can see from the far left-hand column that the laws fall into broad categories. There's environmental protection, wildlife laws, coastal impacts, and pollution control laws, and a rather large bucket of miscellaneous laws. You can see in the top 2 rows, yellow and orange, that across the board, no matter the technology, all federal or federally permitted actions will require environmental review under NEPA, the Endangered Species Act, if a species is in danger of extinction that might be impacted, Magnuson-Stevens Act, if essential fish habitat or federally managed fish stocks are involved, and the Marine Mammal Protection Act, if marine mammals are present. If the activity is going to be closer to shore and affect the state's coastal management plan under the Coastal Zone Management Act, federal actions must be consistent with the enforceable policies of that plan. And if the activity involves installing a structure in navigable waters, then they must receive a permit under the Rivers and Harbors Act. If the activity involves discharging pollutants or dumping materials, then the Clean Water Act and the Marine Protection, Research, and Sanctuaries Act, which is the United States implementing legislation for the London Convention, will come into play. And as you can see from the purple row, there are a number of additional potential laws related to activities on land or operations in state waters or transportation, offshore structures, personnel, etc. And even though I've lumped these into a miscellaneous category, there are a number of laws to navigate there. So what are the prospects of developing new laws and policies that would help establish a path forward for CDR generally, and ocean-based CDR more specifically? This is definitely a rapidly evolving field. Significant events over the past 5 years have clearly catalyzed a shift in interest in CDR, including ocean-based CDR. Starting with the Paris Agreement in 2015, as you know, it set the goal of holding the increase in global average temperatures to well below 2 degrees C and committing to pursuing efforts to limit temperature increases to 1.5 degrees C. Shortly after, the IPCC's 1.5 report stated that limiting warming to those levels would require significant carbon dioxide removal. In the year followed, the global climate community turned a lot of attention to the ocean climate nexus with both the SROC report and the Blue COP. And most recently in the United States, the election of President Biden and the rejoining of the Paris Agreement, it seems that we're entering a new era for climate policy. Here's a list of the recent CDR bills in Congress. You can see that these have also largely gotten bipartisan support. Most of these bills are related to research and development and better coordination among government agencies. Only one, the CREATE Act here, would require agencies to invest in CDR technologies to offset a small proportion of their emissions, essentially establishing demonstration projects. Most of these bills are relevant to ocean CDR. Two of them, the Ocean-Based Climate Solutions Act and the Blue Carbon for Our Planet, are concerned with better understanding natural carbon stores, both coastal and oceanic. And two, the Sea Fuels Act and the CREATE Act involve electrochemical CDR. Notably, the last two bills here were enacted into law, authorizing research dollars towards CDR R&D. These represent fairly large investments in CDR, but it's not clear how much of the appropriated money will go to ocean-based CDR. Where is the environmental community on CDR? Well, natural climate solutions and ecosystem recovery are applauded by all ENGOs. There's enormous effort and investment in advocating for ecosystem recovery. NGOs with ocean programs like TNC, Conservation International, IUCN, and World Wildlife Fund have focused a lot of attention and resources on coastal blue carbon ecosystems, though much of this work is overseas. And interest in oceanic blue carbon is just now being piqued. Overall, there's less enthusiasm for technological CDR in the ENGO community. But importantly, there is a growing group of new small NGOs popping up and filling the void left by the large enviros, such as Oceans Visions. And interest in funders is increasing. Collectively, these NGOs are conducting primary research, advocating for CDR R&D, and identifying policy priorities in this space. Lastly, there is a growing group of large NGOs that are beginning to actively work on CDR, such as EDF, World Resource Institute, and Union of Concerned Scientists. There's a lot of analysis and formulation on internal policies going on. UCS, for example, is in the process of developing a formal position on CDR. There's also a working group on CDR organized by UCS and folks at American University that's bringing together a group of scholars and NGOs interested in more thoroughly exploring CDR. There's less work going on in the ocean space. Aside from ecosystem recovery, ocean-oriented NGOs have remained pretty silent on ocean-based CDR. Above a certain threshold in spatial scale, you lose support from the environmental community for most techniques. This is especially true for large-scale manipulation of biological or ecological systems. Enviros are largely deeply skeptical about utilizing biological systems as carbon farms. This is because in industrialized economies, these enterprises will most likely operate as agro-businesses, and environmentalists have struggled to curb destructive practices in big ag. I'll close with a suite of questions that we have our eyes on as we continue to evaluate ocean-based CDR. And you're all probably familiar with these questions. How much land and water is being used and where? How much matter must be processed for a technology, extracted, transported, dumped? What is the cost and net contribution of a technology to climate mitigation? Does the technology help perpetuate fossil fuel facilities? What are the trade-offs associated with food security and biodiversity? What public processes are being followed to ensure input from key stakeholders? And I'd like to add to this whether or not we have a sense of what proportion of climate mitigation must be addressed through CDR, and can we develop policies to limit what proportion that is? These are all things that we're thinking about at NRDC. And thank you for listening to this presentation. I look forward to having discussion with you in the open forum.
Hello, my name is Kevin Tidwell. I work with the Grantham Foundation and the Grantham Environmental Trust. Today I'm here to tell you about our work in carbon removal, in particular about our work in ocean carbon dioxide removal in partnership with Ocean Visions. First, I want to tell you a little bit about the Grantham Environmental Trust. It was established in 2005. It's a public 501c3 charity in the US. It's focused on combating environmental degradation. And for us, that's almost exclusively meaning focused on climate mitigation and carbon removal. The Grantham Foundation, which is an affiliate charitable organization, and the Grantham Environmental Trust sort of have we have an interesting perspective in a way, because the endowment of both is heavily invested in venture capital. We're invested in over 60 venture capital funds. And then the grant making activities support over 60 leading environmental organizations around the world. And so that perspective is interesting because there's a lot of what we see is that there's, the perspective of venture capitalists, what they want out of a prospective investment. They want it to be, hugely impactful and game changing, et cetera, but they want it all to be done in a short time frame where in the first, 2 or 3 years, you really have to knock down a lot of milestones. Meanwhile, environmental grant makers are really good at funding the enabling environment and policy changes and market development and all these things that are really needed, but are often very reluctant to fund very specific climate solutions. And so we see that there's this sort of gap between, enabling environment and venture capital is ready to support it. And some really sort of tremendous ideas might be in the middle. And we sort of see our primary role in this ocean carbon dioxide removal space to help identify and support those activities in the middle. So first, a little bit about our Neglected Climate Opportunities Program. We set up a wholly owned subsidiary of our public charity that can make mission-related investments. We picked 4 themes that we thought would be big in terms of climate impact, big in terms of scale, low in terms of cost, and heavily underinvested by others. And our 4 themes are seen here: seaweed and ocean innovations, soil carbon sequestration, oil and gas methane reduction, and carbon removal technologies. So we have for 4 years been funding, for example, in carbon removal activities that even if there isn't quite a price on carbon that supports those businesses, we think one day the world will be paying a meaningful price. And we just hope that we can sort of accelerate so that there are more options that might work at that time when sort of the policy catches up with the need. So of the 4 NCO themes, we found that seaweed and oceans has been by far the least ready for investment. And what that has meant is that about 18 months ago, we began to engage with Ocean Visions to say, well, if there aren't great ocean CDR investments ready, what's a way to sort of begin to build the field and have more potential investments for the future? So Ocean Visions, you guys know them really well. Obviously, that's why you're here, but they're really helping sort of develop the ecosystem on what should the ocean CDR themes be, who should be involved, obviously as broad of a network as possible. How do we identify even the right questions to be asking? And then when they're, a particular help that they're providing us is when promising specific pilot opportunities arise, they're helping us assess it. They're helping us identify advisors that will help both make that effort more likely to succeed, but also engage and assess the potential for adverse consequences. And really sort of, you can imagine that over time, it's those suite of experts that are helping us and others decide, is this something that you continue to fund or not? Our priorities, on the other hand, are sort of to build the ecosystem in different ways. We're trying to get more funders involved. We're trying to fund the specific initiatives. We're trying to sort of put a few things out there that others, I think that, I guess, let's say, would trigger sort of additional questioning, additional innovation, just by having started down the path on some of these important pathways. So with Ocean Visions, we picked 4 ocean CDR removal priority themes, 3 of which there's pathways that are, I think, were published this week that are so tremendous and you should read, and we should keep it alive the best we can as a community. We should improve them over time. But for that first effort, there's so many great thoughts, so many great questions that I encourage you all to take the time to read, at least the pathway that resonates most with you. 3 that are the pathways that are mentioned and being published right now by Ocean Visions: macroalgae, the electrochemical CO2 capture, and ocean alkalinization. Those are 3 of ours. The other one that we've sort of been looking at is this idea of carbon negative shipping. Carbon neutral shipping is sort of ambitious enough, one would say, but there do seem to be pretty intriguing ideas that the combination of sort of call it carbon negative fuels or carbon neutral fuels, but then with that sort of mineralization attached to it, may end up making carbon negative shipping possible one day. So I wanted to just give you a few examples with the last remaining minutes of my presentation here. In algal pathways, we've looked at probably 35 seaweed deals around the world, and most, I guess our general takeaway is, in the wildest expectations of the entrepreneur, it still probably won't matter climatically, most of those opportunities. We found one exception that we really like, and I think is on the Ocean Visions website, but a partnership with Running Tide, where this is a sort of very impressive shellfish focused company that had a really innovative idea how to grow macroalgae, how to sink it, how to do it so much more cost effectively than a lot of the alternative ideas out there. And so we provided a company with a side pot of money that says, go try this, and if it works, we'll be your investment partner on that. But it wouldn't, in a normal world, the investors of a shellfish company would not allow you to take some of those proceeds and go try what is a high risk in terms of execution idea. And you would just be sort of focused on your knitting, right? But what we've done here, I think, is bring forward Running Tide's ability to try what seems to be a very exciting idea in sinking macroalgae. And the second theme here, in electrochemical CO2 capture, we have 2 things worth mentioning, one of which was, again, recently announced on the Ocean Visions website, but this partnership with Matt Eisenman, well, let's say Stony Brook University and University of Washington, to really look at how do we directly pull acid out of the ocean, and what would that acid look like? What are the applications to use that acid? How do we scale it? How do we bring down the cost? What are the sort of local impacts of changing the pH as you pull out CO2, or sorry, HCl in that case? And so that's a 2-year effort. It's a grant to Stony Brook University. We hope it goes well, and if it does go well, we'd love to continue to support it with investment capital. Third, seawater mineralization is a UCLA effort that instead of pulling HCl, is trying to pull hydrogen out of it, and the hydrogen helps pay the cost of much of the carbon removal, and is also very early. Also probably 2 years of grant needed before you even really know if this is something that should turn into a company, but seems really promising and exciting as well. In ocean alkalinization, I think Jeremy Lay is presenting at some point at this conference, and we're really supporting him in these early stages of exploration of, are there ways to modernize mining, and is the byproduct of that a sort of safe alkalinity enhancement possibility? And that, again, early stages, pre-seed, but hopefully Jeremy shares what he's up to, but that's also really exciting. The last one to mention is Caltech's effort to help neutralize shipping emissions with the mineralization of those emissions using limestone. And again, we've been granting that idea for over 2 years. And you know, is it ready to be a company? Not, no. But is it still something that one day could have a huge impact in helping shipping industry meet its sort of ambitious 2050 goals? We think so. So anyhow, I just wanted to sprinkle a few of the things that we're up to. We're always looking for sort of new ideas, looking for new partners. This partnership with Ocean Visions has been nothing but wonderful, and we're so grateful for it. And just grateful of this, you know, I felt like 18 months ago, Ocean CDR was not a thing, and 18 months from now, Ocean CDR will be, you know, something a lot more people are talking about. And we're grateful for your interest and help with this. So thank you.
Great. I want to thank all the speakers. My name is Lydia Kapsenberg, and I'm a co-chair with Brad and Dave. These talks have given a great snapshot on the state of the field of ocean CDR, and clearly to reach any climate target, CDR will need to happen. And the question is whether or not we can come together and rise to that challenge. As you see from the panel, this requires many different areas of expertise. So we have a few follow-up questions. Our first one is for Dr. Mazurik. A growing number of philanthropic funders have started to support CDR pathways, but as your talk demonstrated, ocean CDR has received very little attention, but its potential for contributing to large-scale carbon dioxide removal is quite high. Why do you think that is, and what do you think can be done? How can we get more foundations on board?
Yeah, I alluded to this earlier, and thank you for the question. And we've had some experience, and by we, I say Lydia, Antonius, and our amazing removal team here at ClimateWorks, Francis Wong, who's on the call, and most recently Maya Batras. And I think it's twofold. On the one hand, there is a lot of lingering heartburn around the ill-fated iron fertilization efforts that occurred, and funders remember that and don't want to be involved in any of that. I think related to that point are these looming governance questions. They're very, very frightening for philanthropies that focus in the climate mitigation space or ocean conservation space. And then lastly, I think even for those funders that might consider ocean removal, it depends on how one presents the subject matter. As I said earlier in the conversation, I think climate philanthropy really likes to marshal any number of different tools, whether it's empowerment or really ambitious campaigns to stop coal or advance electrification of passenger vehicles. And that tends to appeal much more than some of the more early stage, let's say less colorful approaches that we are discussing around ocean alkalinity enhancement or around, kelp, for instance. And so I think one has to figure out a way to make these topics a little bit more compelling. So for instance, ending offshore drilling is something that really gets climate mitigation funders and some conservation funders super excited. But then when one has a sort of a lengthy discussion about whether kelp sinks to the ocean floor, it's sort of like having an ice cream sundae and then being forced to eat broccoli. And so I think we all have to get much, much better at communicating some of these difficult topics, both the governance pieces, the historic features that are less appealing, and then just having to lay out why studying the science is important to address those earlier concerns. And for that, we have an amazing bench of great communicators working with us in this effort, including former Vice President Gore's communications director, Kaylee Kreider, among others. But communications work is incredibly expensive, and with our modest resources, it's quite difficult to do. Sorry for the long-winded response, but as you can see, mobilizing support in this field is a passion of mine, and with the team, we're absolutely committed to it. And again, this is a young field, so there's plenty of upside growth potential here, and I look forward to collaborating with all of you on this call to achieving that.
Thank you. Yeah, having funding, of course, is one of the first steps to advancing this field. This leads me to the next question for Dr. Suetoni. Given the time pressure for finding CDR pathways, but also need for careful, inclusive debate about the risks, benefits, environmental justice, and equity, what do you think is the most productive way for scientists, CDR advocates, environmental NGOs, climate justice activists, and others to engage in an efficient and productive conversation about ocean CDR?
I think having diverse roundtables is one of the best things we can do at this phase, and having very honest and candid and open conversations. If there, if people detect that there's bias in the room, it could start causing polarization and hunkering down and people taking very conservative positions on the topic. So I think we're at, so far so good, but that we really need to keep our mind open and include all voices.
Great, thank you. This next question is for Dr. Haynes. From your experience working on land-based ocean CDR, land-based CDR approaches, what do you feel are some of the biggest lessons learned that could be applied to ocean-based CDR so we don't, repeat similar mistakes, or any sort of knowledge transfer that you think would benefit this field?
Yeah, I think the single biggest lesson is that measurement matters. That when people want to invest money in doing things, they need to know that the results are actually happening. And ultimately, we're talking about people being paid to do this work. And we've all seen that these are very difficult systems to measure. The ocean is probably harder than the terrestrial systems, and the terrestrial systems are already nasty. And so putting the science in, the AGU community is super important, making sure that we understand how to measure these things, making sure that we understand what the alternative hypotheses for the outcomes might be. So the science is important, but we also have to move forward to these field tests, which has been highlighted already here today, that if we don't get out and test these things, we're not going to know how well they work.
Great, thank you. Our next question is for Dr. Cross. Aside from nature-based solutions like blue carbon and ecosystem restoration, what do you see as the more promising ocean CDR pathways based on the current state of the science?
Sure. I think there's a lot that we don't know right now. So certainly natural solutions are going to be part of that component because we've been studying them for a little while. But I think especially when it comes to NOAA, there's a role for, trying to answer that question as best we can. Which of these methods are going to be able to work? And, like Roger was just saying, which of them can we actually measure? And I don't think, I don't think we have that information or those solutions right now. In part, that's why we need these technology roadmaps so that we can develop the technology to a point that we can actually make a judgment call on what's the best, outside of these nature-based solutions.
That's a good lead in to the next question, which anyone can speak to. Given that ocean CDR approaches rely on large-scale changes to the ocean environment, especially the chemistry, what would a decision framework have to look like that properly weighs the risk and benefits of the ocean CDR approach versus not implementing CDR at all?
I'll start by saying I think there's a misstatement in what you said that the changes in ocean chemistry, et cetera, might be large. I maybe in a very small scale, but one of the things that Ocean Visions has brought to this discussion is the fact that the ocean is a gigantic thing, and that by moving it back to the chemical condition that is its natural state or its recent natural state, is a very small change in the overall ocean chemistry and is beneficial. So I think that the idea that these are major changes that are going to be dangerous is probably something that isn't true. So you might want to back away from that one.
Lydia, maybe just one thing to add on that is that one of the things we talk about a lot, we didn't coin this term, is the no action fallacy. And I think we have to get that really clear from the beginning that there is not a no action alternative here. No action alternative is almost certainly devastating for everything we care about and work on and have tried to protect in the oceans. So we have to compare it against some other alternative that gets us to the outcomes that we're looking for, which is hopefully climate safety, functioning ocean ecological systems, diverse marine life. And for people to say, no, don't do this, I think we have to immediately say, okay, what is your alternative?
Yeah, one of the things that we talk about at NOAA a lot is not just the science, but how do we engage the broader, not just scientific community, but the broader decision-making community and the local public, so that we understand the risks of inaction just as much as the risks of action. All of that has to be a part of an equitable and fair and transparent decision process. And we need to be communicating those things, right alongside. The urgency of this problem also creates an ethical gray area. If we rush the development of CDR, people won't trust that we are doing it properly, and then we'll lose the opportunity to act with the urgency that we need. And so I think we can learn some lessons almost from the way that we rolled out the vaccines, right? We had to take a normally very linear process and parallelize it, which was very confusing for the public. And then on top of that, we had to communicate that that was okay. And so how do we, with the urgency of the climate crisis, just like the urgency of the COVID vaccine development, how do we educate the public on, the safety of these accelerated possibilities? How do we as scientists make sure that we understand the safety of these accelerations, and the safety of this urgency, and then also communicate that? So there's a long way to go with communication.
Lydia, just to build on this for a quick second, we are building technology roadmaps to accelerate the research and development of this field. We're not at the point of advocating their deployment. What we know is that we need CDR, and that there's good reasons that the oceans might be able to provide it, and that they might be able to do so in a way that is really beneficial. So, that part is clear. What's unclear is sort of who might be the or what technology or technologies might be the winners, and whether those winners are going to come from the ocean or come from terrestrial approaches or technological approaches like direct air capture. So I think it's really important to keep that in mind as we move forward and as we launch these roadmaps, that again, these roadmaps are here to accelerate the research and development of these technologies so that we can answer the question about whether or not they are going to be useful for global scale deployment of globally relevant quantities of carbon dioxide removal.
Yeah, I think everyone touched on this need for having many different sectors and expertise and fields involved. And given the diversity of this panel in terms of those fields, what do you all see as the biggest opportunities or needs in terms of these disciplinary collaborations?
I think one of the things that we're going to need right at the outset is to sort of continue, as David was saying, and as we've been talking about in the chat a little bit, we need to continue to develop our observing capabilities. If we can't verify what we're doing, if we can't measure what we're doing, then we're not actually doing anything at all. We might be causing more harm than good. And so to me, like the first baseline thing that we have to do is to continue to develop our observing and measurement technologies to be able to carry out this work.
So Lydia, I just want to jump in with a plug for the maps, which you're going to see in a minute, because they try to highlight exactly what a series of the most critical needs are. And it's going to take a variety of disciplines and a variety of perspectives to meet those needs, right? There's no way this happens with any particular discipline leading the way. This is going to be exceedingly multidisciplinary, multi-sector, multi-perspective. And so the first thing is to make ocean CDR a thing, to elevate it as something that really is valuable as a potential way to do ocean conservation, to get people in academic and oceanographic institutions interested in government and the NGO sector, et cetera, to build these really diverse teams that we're going to need to move each one of the critical opportunities forward.
Great, thank you so much. We're out of time. We can pick up the conversation in the next Q&A session. I just want to thank you to all the speakers again for contributing your talks. And I will turn it over to Dr. Koek, who will introduce the breakout sessions.
Thanks, Lydia. This is the moment that is really, really exciting for us here at Ocean Visions. And I'm just going to wait till a moment until I'm spotlighted and the slide is shared. Great. So this is the moment that we have all been waiting for, the moment where we get to share the Ocean Visions roadmaps with you. So I want to take a moment right now and ask somebody to drop in the chat. Sarah, if you would, please, great, the link to our roadmap. So if you will all take just a moment and use that link that's in the chat, oceanvisions.flywheelsites.com/roadmaps, and load that into your browser, that would be great. So I'm just going to pause here while you all do that. Okay, so hopefully that's all in your browser. And in just a moment, we're going to launch a series of randomly assigned breakout rooms. We'll have 8 to 10 people per breakout room. So please join your breakout room. And once you arrive, I want you to spend each person about a minute introducing yourself. Here at Ocean Visions, we're really about building community. We're really about bringing together diverse stakeholders. And we view this community building aspect as a really, really critical part of driving progress forward in ocean-based carbon dioxide removal. So we want you to get to know each other. So make sure you introduce yourself. And then afterwards, I want you to explore the roadmap. You can do so jointly or individually. And I want you to think about, what is it that you've learned? What is it that surprises you? What do you like? What changes would you recommend to the roadmap? We want to hear from you because as we've made quite clear, these are living documents. They can be changed. So we want to know what's working for you and what's not. And then in the final 10 minutes of the breakout sessions, I want you to come back together as a group, all 8 to 10 of you, and share your thoughts collectively. And in particular, we really want to know about the first order priorities and the development needs. Do you agree with them? Are there things that you think need to be added to them? And how does all this how does all this sit with you? How does it all sit with your group? So with that said, I think we're ready for the breakout rooms. So if you could please, AGU team, please launch the breakout rooms. Thank you very much. And we look forward to seeing you back here when we close the breakout rooms in 40 minutes. So in front of you, you'll see a poll, and please take a moment to answer those questions and hope it gives you a chance to reflect on what you've seen as you've explored the roadmaps over these last 40 minutes. So really curious to see how people reacted to the roadmaps and what their main takeaways were. So just take a few moments and answer that poll when you get a chance, please. And unfortunately, I think a feature of Zoom is that if you join the main group after the poll was launched, I don't think you'll be seeing the poll, but fear not, you'll be able to see the results in just a little bit. I'm going to keep it open for just about another 15 seconds. Okay. I'm going to end the poll now. And then, so you should all be seeing the results right now. You know, what's the greatest strength of the roadmaps? It looked like the connectivity of ideas was the highlighted as the greatest strength, although some people like the display of information and a lot of people like the interactivity as well. That was a really key design feature for us as we were as we set out to build these roadmaps right from the very beginning. We wanted them to be really fun and interactive. From your perspective, what are the first order priorities on target? And people said mostly, the majority said mostly. So this is, again, you know, this is really great to see. We really want these to be interactive, living roadmaps. So if you think that they're mostly on track, but you think that they're missing some key elements, we're really excited to hear from you. And like I said, we'll be launching the feature where people can contribute to these roadmaps in the coming weeks. And then, you know, how would people be interested in engaging with the roadmaps? And this is really great for me to see. You know, it looks like there's a pretty nice balance between people who are interested in working on priorities with others. Some are interested in contributing information, and others are really interested in just kind of reading the information and being able to share it with others in lectures and talks and classes. So that's really great. I'm really, really happy to see that. So that takes us in now into the next portion of our talk. And this is a really exciting portion of our program today, where we're going to hear from technologists who are right at the forefront of building ocean-based carbon dioxide removal ventures. These are a series of 5-minute lightning talks. And so they're going to be fast, but they're action-packed. And I'm really excited, and I hope you are too. And then after that, we'll come back together in community plenary and consider the entire program together. So without further ado, I'd like to introduce Margot Philippi from Running Tide Technologies, who's going to give the first lightning talk.
Hi, my name is Dr. Margot Philippi, and I'm the Director of Ocean Science at Running Tide. Today, as part of the Ocean Visions 2021 Summit, I will talk about the opportunities of working as a scientist in a new venture working to advance ocean-based carbon dioxide removal. Running Tide is building a climate-positive future via aquaculture. Aquaculture can help decarbonize the food industry and can offer carbon dioxide removal, or CDR, via macroalgae, which are also known as seaweed. Running Tide is a startup out of Maine in the US. The company's efforts are focused on oysters production and on seaweed-based CDR via kelp. Oyster aquaculture can decarbonize the food industry because oysters offer natural proteins with very low inputs. The production requires no water, uses very little energy, and very little land. The production can scale to feed more people with fewer resources. The kelp production at Running Tide is focused on carbon capture and sequestration via offshore microfarms. Ocean-based CDR is a budding field that is evolving very quickly. It presents many opportunities to conduct cutting-edge and interdisciplinary research. An example of ocean-based CDR is seaweed cultivation. Seaweed naturally captures carbon via photosynthesis, and it sequesters it when it sinks to the deep sea floor. The cultivation of kelp provides a negative emissions solution that relies on these existing biological processes. The picture on the right shows an offshore kelp microfarm. At the scale needed to mitigate climate change, the solution requires solving several scientific challenges. So what is the role of a scientist in a new ocean-based CDR venture? As an industry scientist, my role is to support the company's mission and efforts. For example, how can we leverage ocean science to optimize the production? How to find the best sites? Can we quantify how sustainable these efforts are, both ecologically and economically? My role so far has been to implement environmental science, geophysics, and machine learning to support these efforts. As a new field in ocean-based CDR, there were no pre-existing roadmaps. This meant that I had the opportunity to take a central part in building this roadmap and setting up the research and development framework. My work so far has consisted of setting up several research and development projects. I have implemented machine learning and artificial intelligence for oyster production. I have designed and co-led several field experiments and selected the sites for these experiments. I have led environmental impact assessments for several of our operations. And a lot of my work consists of oceanographic simulations and analysis for the offshore kelp microforms. Working in ocean-based CDR offers many opportunities, including conducting interdisciplinary research at the forefront of the race against climate change. Climate change needs to be mitigated urgently, and this requires a very fast pace. The impacts are equally high, and the rewards are to solve a problem that affects the entire planet. Startups have several parallels with academia. You need to be resourceful, persistent, and autonomous. At an early stage startup, this means that you also have the opportunity to mold your working environment, and you have room for a lot of science creativity. Finally, working in the ocean-based CDR industry offers the opportunity to collaborate with a variety of professions: engineers, technicians, fishermen, investors, and other professions you may not get to work with otherwise. Thank you for your time and your interest. You can reach out to Running Tide via email at contact@runningtide.com. If you have questions for me personally, my email is margo@runningtide.com. Thank you, and enjoy the rest of the Ocean Vision Summit.
Hello, I'm Beth Zotter, the PI of a $5.2 million RPE Mariner project, begun 3 years ago to engineer advanced offshore sea farms for low-cost and high-yield macroalgae cultivation. This is our team. We have an amazing roster of experts in a number of disciplines, including ocean engineering, robotics, computer numerical modeling, geotechnical engineering, biology, and aquaculture. RPE is interested in macroalgae cultivation for biofuels, but the same goals for scalability, cost, and yield apply equally to any large-scale application for carbon dioxide removal using seaweed biomass. To be a viable CDR solution, macroalgae sea farms must be scalable. That means offshore capable. They must have low capital and operating costs. And finally, they must achieve a high throughput, meaning high flux of carbon through the farm. Our team has developed a suite of innovations to meet these design specifications. First, our farm employs a lattice mooring structure designed for high strength and resilience in offshore conditions. We achieve low installed cost with innovative components and robotic anchoring of helical anchors in deep water with an ROV. Finally, we achieve high throughput and high biomass yield with wave-driven nutrient fertilization using hydrofoil upwellers. Combined, these innovations create multipliers for cost and performance that lead to a step change in the potential for large-scale carbon dioxide removal using macroalgae. To be truly scalable, a farm design must hold up in fully exposed ocean and survive high storm loads. Our farm was developed to scale to 1,000 hectares. It employs a modular design that scales proportionally with depth. Dynamic modeling shows that the lattice mooring structure efficiently transfers loads directly to the seabed, reducing structural mass requirements and materials expense. We'll soon be deploying a 2x2 array in the Gulf of Maine in partnership with the University of New England. This video demonstrates the performance and resilience of the structure in a 25-year storm. Next, to achieve low cost, in the lattice design, helical anchors embedded in the sediment are shared by neighboring modules. The helical anchors are driven into the sediment by an ROV and support loads from multiple directions. Instead of rope, our design uses high strength for weight fiberglass composite line. These stiff materials have a high bending radius and are intended not just to provide improved cost and performance, but also make the farm safer for marine mammals. We're currently field testing a rig with both of these component innovations. The data we collect from our split shaft multi-line anchors and fiberglass composite lines will be used to improve the 2x2 demonstration array. Helical anchors are currently limited by the need for either divers in shallow water or expensive barges with surface-powered hydraulic motors. This early prototype demonstrates the ROV installing a 6-inch helical anchor into the seabed. Our full-size ROV delivers major advantages in both speed and cost. It enables helical anchor installation in 10 times deeper water and faster with small and nimble surface vessels. The ROV is a cross-cutting technology enabler that will lower the cost of offshore farms and a suite of other types of marine infrastructure and equipment. This year, we demonstrated a commercial scale ROV with a pulsing mechanism that multiplies the ROV's torque output by a factor of 5. Yield is the #1 driver of competitive economics in almost every techno-economic model of biomass production, and high yield is our goal. Because nutrients drive yield, we designed high flow rate upwellers to bring deep water nutrients to the surface using wave energy. The size of the upwellers scales with depth and can be tuned to optimize pumping in small waves in summer, when nutrients are most scarce and sunlight for photosynthesis is abundant. In certain applications, upwellers can be powered by a solar panel array. As shown here, the lattice structure allows for wave-driven nutrient upwellers to be integrated into the voids under each node buoy. We recently tested an upweller in one of the University of New Hampshire's engineering tanks. In the ocean, the upweller is driven by the movement of a surface buoy. The hydrofoils on the rotor create lift on the upstroke, generating a vertical jet flow to the surface. On the downstroke, the blades feather to minimize resistance. This design is lightweight, powerful, and low cost. At the surface, the plume of cold, nutrient-rich water fertilizes the macroalgae. An array of upwellers located throughout the farm can supply nutrients to enhance biomass yield throughout the year. The next step in our R&D is to measure the plume dynamics and nutrient flow in real ocean conditions with large diameter rotors. The driving factor in all of our work is economics. Our techno-economic model projects that together, these innovations can bring the cost of macroalgae production to less than $80 per metric ton of CO2, making it very interesting for large-scale CDR. We're looking forward to the demonstration of all these innovations at meaningful scale in the next year. We'd like to thank you for your attention, and also a special thanks to RPE for making this work possible. Cheers.
Hi, I'm Kelly Earhart, Director of Development at Project Vesta. So excited to be here with you all today. So at Project Vesta, we are focused on advancing the science of carbon removal through coastal carbon capture. And in many presentations, I would normally go through the whole process, but this group is well-versed and well aware of how the carbonate silicate cycle works, I'm sure, and how olivine sand placed in coastal waters can accelerate the Earth's natural long-term carbon capture process. As you know, we're working on researching a form of ocean alkalinity enhancement that involves transporting olivine, volcanic mineral, to coastal areas and allowing wave action to accelerate the carbon dioxide removal there. We're calling this coastal carbon capture. It's work that's based on about 30 years of lab research and, of course, billions of years of Earth research. It's important to note that we have begun calling it coastal carbon capture. We shifted from coastal enhanced weathering because when we were talking with lay people, it seemed it didn't mean much, and this kind of made it easier to understand. So a little bit about our roadmap from a high level. I will share these slides afterwards so you can all take a deeper look at this, but just to note that we are in the foundation stage and really excited to share with you some of our recent studies. We're taking a very slow and rigorous approach on our work to ensure that the science is fully validated before any scaled deployments take place. So some of our lab studies that are currently ongoing are within the fields of ecotoxicology, which I'll share about, kinetic studies that are refining the olivine dissolution rates, flume and shaker experiments to develop models of olivine grains when in motion, and mesocosm experiments that are determining potential ecosystem level effects on coastal systems. One of our studies that we're working to deploy is in Papakolea Beach on Hawaii. We're collaborating with the University of Hawaii in Hilo on this study. It's one of 4 natural olivine sand beaches in the world. And so we're really looking forward to testing the natural rate of olivine weathering, carbon dioxide uptake, precipitation of any secondary minerals, and effects on ecology and biodiversity. We're just waiting on a weather window to begin this project, but it's set to happen soon. And then ecotoxicology. So recently we received results on our first ecotoxicology test and it went great. We put these very sensitive juvenile worms in 100% olivine sediment after much back and forth of should we do 1% or 2% or 5% or 10. And we decided to see what happens when we do 100%. And it turned out that we actually got 100% survival in 100% olivine solution. Olivine sediment. So the first test was as successful as possible. And our next experiment is beginning in this week of May 10th. We have many future studies on ecotoxicology to come as well. Now to share a bit about our olivine modeling work. So we're looking at theoretical changes in pH, alkalinity, silica concentration in pore water. So we've simulated the effects of spreading a 2-centimeter layer olivine on beaches. And this results have been interesting because they're showing that there will be measurable effects in the pore water. It's predicting that there will be measurable effects in the pore water. So great news for our larger scale experiments. And critical to our work right now is public acceptance studies. So, there's obviously numerous potential benefits to local ecosystems and communities. So we believe, that it's very important that we engage local communities first and foremost, so that they're also informed of any of the potential risks that we're testing for. So we're working with local people to, create local stakeholder maps, build question frameworks about stakeholders, bringing in local reputable individuals as our community engagement managers, and connecting with local social scientists for specific guidance, as well as conducting workshops. We're also doing some broader social license research on a more global or policy scale. And of course, there's so much for us to do before we can put olivine on the beach anywhere. So, but because of long lead times that it takes to get permits and organize field scale trials, we're already engaged in this process and we're making really great headway. So we've obtained the government permits for stage 1 baseline sampling and have strong government supports for the second stage, where we will actually deploy olivine on the beach at our very first site in the Caribbean. And we're measuring ecological effects, carbon dioxide removal rate, and also creating an integrated assessment model out of the data that we'll get out of this first demonstration site. We've made lots of progress from everything from, the Stripe purchase that we had in 2020, whereas the first purchase of negative emissions credits through coastal carbon capture, submitting an initial position paper to the IPCC, adding more scientists to our team, and really exciting, completing phase 1 fundraising in 2020. And today, after having started phase 2 fundraising, we've raised almost $5 million in philanthropic funding. That's kind of what we've been up to in a nutshell. Once again, I'm so happy to be here with you. We've been engaged with Ocean Visions in the production of the first draft of the Ocean Alkalinity Enhancement Roadmap, and we're so excited that it's launched. Really look forward to helping it progress, develop, and hope to collaborate with others doing similar work. Once again, I'm Kelly Earhart from Project Vesta. Happy to be in touch with any and all of you. You can find me on LinkedIn or email me directly. Thanks for all your work on ocean regeneration and carbon dioxide removal.
Hello, everyone. I'm Jeremy Lee. I'm the CEO of Negative Emissions Materials. And today I'm going to talk about why we're trying to make magnesium hydroxide to do ocean alkalinity enhancement. The oceans currently store 40 times as much CO2 as the atmosphere, 50 times as much as the biosphere. And so there's an interest in whether or not we could leverage this fact into climate solutions. The emerging consensus is that actually solving the ocean acidification issue, which is the other CO2 problem, could, as a byproduct, deliver carbon dioxide removal at the very large scale. This is theoretically sound, but there are obviously risks associated to this. And so the scientific community is working on those risks, and in particular, the ecosystem risks of what would happen if you were to add alkalinity to the oceans. And it, of course, depends on what kind of alkalinity you add. So this leads us to the third part of my presentation and why we are focusing on hydroxides and not just grinding rock and adding it to the oceans. The reason for that is that two of the major risks identified by the scientific community are adding iron, silica, and other metals to the ocean, because this would stop the presence of these elements in dissolved forms in the oceans being a limiting factor to the development of some species, and this could completely unbalance the species and the ecosystems and the food chains in the environment of the oceans. So just to make that clear again, by focusing on hydroxide, where you have only the alkalinity, the OH, and a cation on the other side to carry this into the sea, you are avoiding additions of silica and metals, such as iron, which could have negative impacts on the ecosystems. The other advantage of hydroxide is that they are probably more reactive and give you better kinetics and dissolution rates. Now, the last point that I'd like to make is, why are we focusing on magnesium hydroxide and not calcium hydroxide or sodium hydroxide? So caustic soda or lime, quicklime. The basic reason is we have focused on magnesium units which are linked to a very abundant source. And it turns out that magnesium silicate rocks, which are non-carbonated, so not linked to CO2, are very abundant on the planet. Whereas if you were to look at calcium, for example, most of the calcium units on the planet are associated to carbonates. So calcium carbonates, think limestone, think building blocks, think cement. And so the challenge of those approaches, calcium, for example, calcium-based approaches, for example, are that they're going to generate CO2 by splitting the calcium carbonates into a calcium oxide and CO2. And if they are to capture that CO2, that's going to penalize the economics. Whereas in the magnesium silicate situation, there is no CO2 to recapture. There's another advantage in that, is that when you're doing the magnesium silica splitting, you are also getting a silica or a metal product on the other side that you can market to carry the cost of the system. Whereas if you're doing this in a calcium carbonate system, for example, once you've added the calcium hydroxide to the sea and you've captured the CO2, you have nothing left. So to summarize that last point, we've focused on magnesium hydroxide from magnesium silicate rocks because we think this is the most cost-effective way of doing it. That would be happy to be proved wrong. To summarize everything I've said today, so what led us into this space is the belief that there needs to be more investment in carbon dioxide removal technologies, that the oceans seem to be a promising place to work to do 100 to 1,000 tons, 1,000 gigatons of carbon dioxide removal. We focus on hydroxide to minimize any kind of potential risks to the ecosystems and to the marine environment. And lastly, we focus on magnesium hydroxide because we think that by focusing on magnesium, we can do this in a cost-effective way by marketing the co-products of this magnesium silicate ore processing, and by avoiding the CO2 recapture costs of, for example, ocean liming. Happy to take your questions. Thanks again for your time.
Hello, everyone. My name is Daniela Fernandez, and I'm the founder and CEO of Sustainable Ocean Alliance. We are a global nonprofit that supports young people in creating ocean solutions and also accelerates existing solutions that will help heal our ocean. We bring together entrepreneurs, advocates, mentors to be the solution for our planet and ocean. A little bit about how this started. I was a freshman at Georgetown University at the age of 19 when I realized that there was two big missing components from this ocean conversation. One of them being the importance of incorporating young people into these conversations, and two, bringing innovation, entrepreneurship into these opportunities to build new technologies to figure out a way to actually solve for these problems instead of just talking about the gravity of what's at stake here. Here is an example of our global reach. We actually have young people in 165 countries. We provide access to microgrant funding to our young leaders, also access to funding to our entrepreneurs. And here is a little bit about how our program works. We have an accelerator program that supports entrepreneurs that have a for-profit, scalable, and impact-driven solution. We give them access to mentorship, guidance, funding, and resources, in addition to access to our investor network where they can go forth and find investment dollars. The second program we have is our leadership program, which focuses on supporting young leaders that have an idea or an initiative that they can implement in their own community. We give them access to microgrant anywhere between $1,000 to $10,000 to bring their solution idea to life. And last but not least, we also have our movement creation, in which we open the doors for any person, whether it's a mentor, an investor, a scientist, an advocate, to join our movement and help us uplift these individuals, these young leaders, and these entrepreneurs. So in the theme of our conversation today, I think it's important to take a look at these sectors within the ocean space that are so ripe for disruption. First of all, looking at renewable energy, we know that we can do so much more globally to improve what we're putting out into the atmosphere. So instead of putting carbon out by using fossil fuels, we should look at technologies such as CalWave Technologies, one of our startups through SOA. They're actually using the waves energies to produce renewable energy as opposed to relying on dirty fuel. So that's just one example. Also looking at the maritime transport industry, there is a mandate that has been put out there by the IMO demanding or asking these shipping companies to decarbonize. So these companies are going to need a lot of innovation help, a lot of support to make this happen. So it's up to all of us to figure out a way to get this industry to meet these goals as soon as possible. And the three last industries here to talk about are fisheries and aquaculture. We need to find ways to fish more sustainably. We need to find ways to replace plastic as this toxic material that goes into our ocean, into our water, with a sustainable alternative. And also looking at marine tourism. How can we plant more mangroves? How can we improve the way our coral reefs are growing and not decaying? How can we build more seaweed farms to have our ocean continue being that carbon sink it acts as opposed to depleting it? At SOA, we have this goal by the end of the year to have accelerated 100 ocean solutions, and we're very excited to be on the way to make that happen. You know, one of the interesting learnings from this journey is that we've had to educate not only young people about this mentality shift of being a victim or being a bystander to what's happening to our ocean, and instead being an active contributor, an active solutionist, an entrepreneur. And so that's the journey that we've been on with our community, and also having to educate investors about the ocean space, about the opportunities that lie in this innovation space that we are all working towards, to fill in the gap and achieve. I'll just give two very brief examples of the companies that are contributing to these carbon solutions. One company, Lydia, what they're doing is they're replacing plastic with seaweed material. And so not only are they solving for the plastic problem, but they're also solving for the carbon problem by using seaweed farms to suck in some of that carbon and acting as a carbon sink. Another company that we have supported, they're called the Returning the Lost Forest. They're actually a microgrant project of SOAs. And this micrograntee has planted 4,000 new mangrove seedlings and is working in partnership with different countries around the world to help replicate this technique and make it more successful. So again, those are two examples of carbon solutions we have in our network. We have so many more, but given the time that we have here, I will end it there. And feel free to reach out to me for more information. Thank you very much, everyone.
Okay. Thanks to all of our lightning talk speakers. Those were great, great presentations, very thought-provoking, a lot of really interesting information. We have about a little over 20 minutes for a general conversation. I'm hoping that we can get all of the panelists who are here spotlighted in a Brady Bunch or Hollywood Squares for those of you in my generation format here. And we are gonna ask some questions. So I've pulled the audience for some questions. I have a few questions as well, but I like this one right up front, and I'll start with those of you, because everybody answers brief, but what would be the one thing, if you could choose one thing that would really make your work go a lot faster? And why don't I start with you, Kelly?
Did you say start with me? Hi, I'm Kelly, and I'm joined here with Steve, one of our senior scientists at Project Vesta. At Project Vesta, one thing that would really make our work happen faster would be more policy and regulatory support and partnerships in that space. For us, I think one of the hardest questions is when it comes to permitting and moving things forward in a way that we can perform some of the initial baseline experiments that are necessary and have access to do the initial experimentation that we need to do to get the project off the ground. So looking forward into the future, I think policy support, regulatory frameworks that can move forward ocean-based carbon dioxide removal solutions are going to be really crucial. And it's a large question that we're looking at, as I mentioned, around our our social licensing studies, both locally and then at the broad scale. It's one that we're incredibly interested in partnering with organizations to try and advance our work in.
Great, thank you. And I'll just point out one of the upcoming maps. We only released one map today, just at a time, but one of the upcoming maps is on governance. Social political considerations and governance, which are all very much wrapped in. I'm going to go to Margot. Additive to that, what would be one thing that would make your work go faster, bigger, better?
I think the policy framework is key here as well. Just policies, permitting, trying to work with different stakeholders and say, we're trying to do something environmentally friendly here. Can we please have more research permits? Can we please do this closer to, shore and so forth? On top of more technological development beyond just microalgae, we're doing a lot in the space of material sciences. For example, it would be great to see this type of environmental initiatives in other aspects of science as well.
Thank you. And Beth, you are the other entrepreneur on the panel. How about for you?
Sure. Yeah. I mean, I hate to be like a broken record here, but yeah, getting research permits that have different criteria than commercial long-term projects, I think is critical. Having specified zones for doing ocean engineering and advanced research would be a huge step forward in cutting a lot of the red tape and not making people repeat the efforts. There's a lot of duplication of efforts, and there's a big opportunity to streamline those permitting efforts, and of course, more funding. always,
thanks. So building on that about governance, and we saw the presentation from Lisa and the plethora of regulatory frameworks that govern what happens in U.S. waters. I want to go first to Jessica and then Lisa. Jessica, for the government, what can we do to create an enabling regulatory framework for this work?
As a scientist, I am very specifically not a manager. And that's a whole nother wing of NOAA's activities that I hesitate to comment on behalf of the agency.
Okay.
I do think there's an opportunity to sort of help streamline some of these regulatory questions that we've been talking about in the government space through the agency, but that's really the best that I'm going to be able to do. Lisa?
Well, hold on. Before Lisa, I'm going to come to you, Lisa. Roger, you're also associated with this on the terrestrial side. You may have some observations on if anything has worked terrestrially that has sort of made it easier to get to the kind of experimentation needed.
Yeah, one thing the agencies can do is to create sites where these things can be tested, where much of the regulatory work has been already done and shared by everybody. And it means you have to share your results, but we're all trying to save the planet. But I think these test areas where these things have been done by somebody else and where an entrepreneur can come in and take advantage of that are powerful tools for advancing.
Thanks. Okay, Lisa, so from your perspective, and especially representing the NGO environmental community, what do you think makes sense in terms of trying to enhance the enabling regulatory framework?
Well, I think it makes sense to come up with some environmental guardrails. I think what most people are afraid of is the impacts of research. And so if there were strong environmental and social, et cetera, guardrails that that were established for the research, then people would be probably more comfortable in establishing it. easier to get research permits. But I do think there's a tension. I think it's pretty important to identify. There's a tension between social license and acceptance and trying to get over existing environmental regulations. I mean, if this movement is seen as a movement that wants to accelerate by avoiding environmental hurdles, then there's going to be some backlash, and that could have a real decelerating, effect.
Right. Okay. Thanks. That was helpful. So there's another set of questions here just around measurement, which I believe, Roger, you might have ended your talk with saying was one of the most important things. It's identified in the maps. I know Dave has spent a lot of time thinking about measurements and sensors. One of the questions here is, how can we collectively pull together the information systems, maybe the sort of Internet of Things combined with the right sensors and the additional things that we need to have an idea of what happens to carbon in these different ocean sequestration pathways. And Dave, maybe I'll ask you just to start first with what we learned from the roadmaps about that.
Yeah, thanks, Brad. One of the things that we highlighted in the roadmaps under the controlled field trials subcategory is the need for greater integration of data and models. So we have academic models right now. They're not very accessible to lots of people. Some of the research grade sensors, it's almost like you need a PhD to operate them. So we need to dramatically expand the number of really high quality, easy to use sensors. And we need really easy tools that allow people to take that set of ocean observations from this new class of sensors and integrate them seamlessly with models. And that's going to be important for two reasons. It's going to be important for designing really well thought out field trials and understanding what we need to measure and where, both to test the field trials and to validate aspects of carbon sequestration and permanence. And the second thing is, of course, from an operational perspective, it's too labor intensive to keep people out at sea all the time. So we need really robust monitoring, observational tools, and modeling tools so that we can support autonomous operations.
Thanks. I'm wondering, Jessica, do you want to add anything to that from the experience of the Acidification Observing Network?
Sure. I think that one of the things that I'm starting to hear more about, just like David was mentioning in his comments right there, is the idea that we want to try and daisy chain as many of these new methods as possible to try and come up with like a really good pathway forward, right? We want to pair alternative energy alongside carbon removal, alongside our existing infrastructure, alongside places where we have, the regulatory capacity to do this work. And so we're sort of looking for these unicorn projects, right, that all fit, as seamlessly as possible into the existing space and infrastructure. And I think those opportunities will become apparent and available. I don't know that we know what they are right now, but the more we figure out exactly how we want to do this work, down to the really refined scale of, well, we're going to attach this to this, to this, to this, and that only fits in this particular puzzle piece hole over here. That's really where the opportunities are going to emerge. Once we have that kind of proof of concept study, I think we'll be able to expand that a lot broader. One of the things that we need to be able to maintain is our current global observing network infrastructure to be able to develop, the baseline measurements that we're going to be trying to measure CDR against. But there's also a lot of areas that global observing network doesn't cover. And so we're going to need to really initiate and scale up a coastal observing network that's capable of seeing these CDR projects on a really small scale that, the global observing network can't resolve right now. And so daisy chaining these methods, thinking about working more coherently at the coast, though, that's where I think our technology development opportunities are going to be, our observing opportunities are going to be.
Shifting gears, there's a great question here about what advice we might give to high school students listening to this presentation about what skills, competencies, knowledge they should develop. I'm going to turn this to Daniela and maybe think about college students, because we have a number of university members and we have a lot of early career professionals. What do you think are some of the skills and capacities that people need to be developing to be players in this space of solutions.
Thanks, Brad, and I'm glad someone brought up that question because I believe that in the environmental and ocean space at large, there's been this narrative that you have to be a scientist or a marine biologist to help protect our ocean, and the reality is that that's not the case. You should specialize in whatever area you're passionate about and whatever area you have a growing skill set in, and then you can contribute that skill set to the ocean. Looking at our solutions at SOA, we have artists that are working on graphic design for these companies, right? We have accountants that are working on the financing to support these entrepreneurs. So as long as you have that North Star, which is protecting our environment and our planet and our ocean, I would just encourage you to really become self-aware of what your real passions are, what your inclinations are, as opposed to simply going down the traditional path of, majoring in marine biology, going to grad school, then getting a real job and going down the path, because in reality, we just don't have time for that anymore. And that's why I started SOA at 19, because I was told by people, go get a real job, make money, and then be a philanthropist and donate it to nonprofits. But by the time I got there in my 50s or 60s, we wouldn't have a planet anymore, which is why I decided to instead start my nonprofit and, I'll build this platform for other young people. So that would be my advice, is start now, understand how you can contribute, and then also build a village, right? There's so many people in the industry that want to be mentors, that want to help your idea come to life. So don't be afraid of asking questions and getting the advice that you need, because no one has it figured out. And that's, I think, one of the biggest realities for any entrepreneur or person out there, to realize that you have a community, so use it.
Great, that was a great answer. Thanks. I want to turn to this topic that's sort of been kind of in the background and dominating for quite a while, which is the social political acceptance. I think a lot of us here feel like what we're doing is trying to save the planet. Obviously, not everybody sees it that way. What would be, one or two sentences that you would say about why this work is essentially mission driven or ocean conservation? What's the talking point that we can use to help turn the conversation about ocean-based carbon dioxide removal? And Margot, let me start with you. I know it's a tough question. You're on mute there.
Sorry, I cut out for a while. Could you please repeat?
Yeah, just what would be the one or two sentence answer you would give to somebody about why the work you're doing is so important for the future of the ocean? How do we start to build the language, the words that we need in order to help this field resonate more as conservation?
Yes, I guess if I were to see any person on the planet, I would start by telling them that about 50 to 80% of their oxygen comes from the ocean. So when you look at carbon dioxide as a pollutant, it needs to be removed, because this is a pollutant that affects all of our food chains, but also that disturbs the structure of the phytoplankton, which, is kind of like the lungs of the planet. So if you're a human being and you breathe oxygen, which you're very likely to be doing, you absolutely need to protect this. You need to protect these food chains. You need to protect our climate. There's going to be a very, very disruptive, a lot of disruptive changes in weather patterns that are going to have absolutely astronomical repercussions for geopolitics, for any, really any society as we know them. So I think that it goes well beyond the ocean and well beyond, solely some niche environments or some niche ecosystems. We're all going to be impacted. And I think last year was kind of a prime example of how we're absolutely not ready as a society to face these type of major global disruptions.
Thanks. Kelly and Vesta, what do you say? What are your talking points about carbon dioxide removal as a key part of the equation?
Yeah, I would definitely echo what Margot said there, especially and especially at the end of how you pointed to the way that coronavirus pointed out the fragility of our sort of like resilient systems as a society, as a global society, and the interconnectedness that we all can either benefit or suffer from. If depending on how we choose to work within this environment. And I think the main point that we like to make is that through ocean alkalinity enhancement, we are actually just helping the ocean do its job, one of its primary jobs of being a natural carbon sink, sequestering carbon dioxide, and turning it essentially back into rocks. And so by increasing the alkalinity of the ocean, we're able to sort of increase the buffer capacity and just help the ocean keep doing what it does really, really well. So a large part of what we like to communicate is working with Earth's natural systems and sort of being stewards of enhancing them.
Excellent. Beth.
Yeah, I mean, the way I think about the ocean is the Earth's largest bioreactor. Just even a small change can have huge impacts, right? And you know, the biology is one aspect to how we can present solutions to this problem, but it's one of the most powerful. And you know, I think that's pretty compelling. People don't think about how we can use the ocean, and that's when we're talking about technology. We're talking about applied science. How can we use the ocean to benefit the ecosystem and human society and help bring our climate back into manageable equilibrium.
Thanks. I'm going to ask one more person on this one. Lisa, what would you suggest would be a point that would resonate?
So I'm going to be a little bit more of a skeptic. I'm not sure that it's a great idea to sell ocean-based CDR as ocean conservation. And I think that gets back to kind of the original question you asked me, which is if you start to look, I think there has to be some objectivity in the conversation, and that we need to approach this very major crisis with very rigorous science and say that the ocean may be able to help with this problem, but if it's to do that, we need to be able to measure it and verify it. So I keep on coming back to applying a lot of rigor and healthy scientific skepticism to all of these questions, because if it's not measurable and if it's not verifiable, it could actually make climate change worse. And so I just think we should stick with that very, very scientific, stodgy skepticism for now. How's that for someone who was trained as a scientist? Sorry.
No, I think that's completely appropriate. I think everybody, I don't want to speak for everybody, but certainly Ocean Visions is focused on trying to answer the question of whether these things can contribute. Not until we get to that, until we get to that answer, we're just, we're not ready to commit to deployment, but we feel that the urgent need to accelerate to get to that answer. So shifting gears, and this is really probably the last question, I'm going to ask just a couple of you. Ocean Visions is this network of research and academic institutions and a series of private sector partners. What do you think, what would be the best contribution that Ocean Visions could make to the work that you're trying to do? And or this kind of shared mission of trying to determine whether ocean CDR is going to be a thing that is worth doing. Maybe I'll start with Roger.
I think encouraging this discussion has been incredibly valuable, but I think, and I think that the bringing this message to the skeptics with the background of environmental activism is very important. The idea that this is not Exxon bringing this solution forward. This is people who care about the ocean bringing it forward. And I think you have to keep hammering on that, because the public trusts organizations like that, and they need to hear that message that, your no action alternative statement really resonated, I think, with a lot of us. That people need to hear that.
All right. Well, we are at the end of our time. We have one more quick poll that I think is going to come up on the screen before we close out for the day. While it does come up, I just want to thank all of you for your time, for your honest engagement, for your input. It is super useful. I want to thank everybody who tuned in this session as well, because we are very glad to have you and we want to work with you and build community together. So hopefully you can see the poll now. Seems to be taking up my whole screen. So just take a minute and answer it. All right, AGU colleague, how much time left on the poll?
We have 75% weighing in. I can shut it down when you're ready.
Okay, why don't you go ahead and shut it down and let's see what it looks like. All right, so basically this is really about what we've been talking about. You know, do we have confidence that this community will be able to test and evaluate and pilot CDR methods in a socially and environmentally just manner? You know, it seems like there's confidence that we're on the right track, at least with about 10% of people not too confident. So, you know, that's better than it could be. I think it's actually pretty good for where we are. We could have healthy dose of scientific skepticism and move forward accordingly. So we're now going to close this out. I'm going to let Dave make a few closing comments before I close the session. So Dave.
Thanks, Brad, and thanks to all of you. It's so great to have seen so many colleagues and to meet so many new people today. I'm really, really thrilled to have reached this point. This is a really significant point in the development of Ocean Visions. You know, when we set out to launch this project a year ago, I just could not have imagined that we would have reached the point where we would have nearly 300 people at one point on this session listening to us as we roll out these carbon dioxide removal roadmaps. And I just want to circle around to one point that came up in the community plenary. These are roadmaps to accelerate the research and development of ocean-based carbon dioxide removal pathways. Ocean Visions is not advocating that we go out and deploy these at globally relevant quantities right now, but Ocean Visions is advocating that we need to take the steps necessary to develop a comprehensive and robust research and development plan. And this research and development program is not going to just encompass the science and engineering around macroalgae development. As we've said, there are 5 roadmaps that are rolling out, and these include one of the roadmaps on growing and maintaining public support. So this touches on aspects about policy, governance, public perception, and many of the things that came up in the community plenary. So I urge you to stay engaged. I urge you to watch out as we release these additional roadmaps. And I urge you all to help contribute to building this community together. This isn't just Brad's and my project. It's not just Ocean Vision's project. It's all of our project. And we built that platform to be able to handle it. So thank you all very much, and I'll turn it back to Brad.
Thanks, Dave. I think you echoed or said some of the things that I wanted to touch on, so I won't repeat them. I think we are I'm really excited about the maps. Only one of them was live today. 4 more will be live over the next 4 to 5 weeks. We are integrating the oceancdr.net website into Ocean Visions, and registered users on oceancdr.net will be able to become registered users on the roadmap site, which means actually contributing to particular aspects of the map, of the work outlined in those maps that you want to contribute to, and being engaged with other people, and actually being able to find other people around the planet who are working on the same things that you might be working on. So the idea of these maps is really to build a community and to build momentum and collective action around the kind of work that we need to do very quickly to determine whether ocean-based CDR is going to solve some of our CDR problem. The one part that's not on the table for us or the IPCC is that CDR is absolutely necessary. That part is not really debatable from a scientific perspective. even from a political science perspective. But where we get it is what's really open, and our contribution here is to look at the oceans. And so thank you again for you joining us today. Thank you for continuing to be involved. And by the way, there's 5 more major sessions coming up in the Ocean Vision Summit in the next few days. And there are networking sessions, there are poster sessions, and there's in fact a series of papers being presented on this topic that we weren't able to highlight today during the session. Those are available. If you go on the main program, you'll find the links to those. And in some cases, you may be able to meet with the authors and speak with them. So I encourage you to do that. Thank you all. Have a great conference, and we will see you at one of the upcoming sessions. Bye-bye.